Warm welcome on behalf of 5G-ACIA to our today's web seminar session. Let's check whether people are still joining, but I guess quite most of them are here. We had some last-minute technical issues because the colleagues from Fraunhofer, they are preparing a live demo, but we will see that shortly. But before we start, I want to introduce myself. I'm Lisa Underberg. I'm with the Institute for Automation and Communication in Magdeburg, and I am the Working Group 5 chair. Working Group 5 in 5G-ACIA is the working group hosting the Endorsed testbeds. And today we are going to hear about two of our testbeds, which are already finished or almost finished, and we will see how they applied industrial 5G in their respective use cases. Just for some general information, please feel free to ask questions via the chat window or the Q&A window. We will address as many questions as possible in the end of the web seminar. So we are going to hear both talks, and after that, we will attend to the questions in the chat. If any questions remain open, you can become a member to get it answered, or first try to get in touch via the office or to us directly to discuss your questions bilaterally. The recorded version of the web seminar will be made available afterwards. This is why everyone except for the speakers should be muted. And if you experience technical problems, you can also reach out using the chat window or to info@5gacia.org. That's where our office colleagues will attend to your problems. So we will have a couple of live polls where we are, or would be happy if you answered them. They will appear in the chat window and probably, depending on your Teams version, also as a pop-up. So to get that started, let's practice that before we have them in our talks. At first, we would like to learn a bit about you as our group of listeners, and we would be interested to which stakeholder group you belong. Now, I think the office is about to start the poll. I also need to check a bit where to navigate. Answers are coming in. So we have, we plan to have 20 to 40 seconds, depending on how long you take to participate, to answer the poll, and then we will move on. So nice. It looks like we have 20 answers now, quite diverse, lots of OT, which is very nice to see, since the application of industrial 5G is most interesting to the OT groups. Okay, let's move on. Second live poll, which region do you come from? That should be an easy one. While you were still thinking, well, am I end user or OT? The region you're dialing in from should be quite clear. Answers are starting to coming in. More answers already, 30 answers. Mostly Europe, a bit Asia. That was something to be expected. Bit North America, very nice. Okay, as we practice that now, without any further ado, let's move on to our first talk. It will be given by Nils König. He's with Fraunhofer IPT. Just as Niklas Beckmann is. The only special thing about Nils probably is that he's also the working group 5 vice chair in 5G-ACIA, but here now today on behalf of the testbed, where we will see 5G applied for sensor technologies, sensor applications. Nils and Niklas, the floor is yours. Share your
thank
screen.
you very much for the introduction. So I hope you can see my screen. Okay, so so we have been dealing with a testbed called 5G Industry Campus Europe, which is our still our testbed. But in the testbed activity, which was endorsed by 5G-ACIA, we are focused on 5G sensor technology for process monitoring and manufacturing. So, and I'd like to first explain a little bit some background about the testbed, and the technical setup will be explained by my colleague Niklas. So first of all, the 5G Industry Campus Europe is still an operational testbed. Yeah, so it's a large-scale testbed in terms of that we have 5G coverage in different shop floors, so 5G indoor coverage, 3 different shop floors, which are completely equipped with different machines and robots. So in total, it's 8,000 square meters of shop floor, which is covered with 5G. And also we have an outdoor network, which is carrying the same network code, and it's actually the same network with seamless handover capability. And it covers in 1 square kilometer of the campus of the Aachen University. And so in terms of the network technology, we are using both 5G NSA because we started in 2019 already. So it's a rather old testbed in terms of it's in operation since 4 years. And also we operate 5G-ACIA in parallel, and we are using the spectrum 3.7 to 3.8 gigahertz, which is very common right now in Germany. Which is not so common is millimeter wave coverage. So there are only a few licenses being granted yet in Germany because it's, let's say, a new technology, and you need to have a look at which kind of use cases are applicable for millimeter wave. So we're using 800 megahertz of licensed spectrum here also on the shop floor, which is subject to another testbed, which will be explained in April. And so since we are using NSA as well, we also have a 4G anchor band, which is band 40 right now. So the 5G Industry Campus Europe is one of the so-called 5G model regions of German government and received funding from the Federal Ministry of Transport and Digital Infrastructure. And Fraunhofer IPT is coordinating this activity. And we have 2 other research institutes in production technology, the WZL, which is the Laboratory for Machine Tools and Production Engineering, and the FIR is the Research Institute Industrial Management. Our network partner and supplier is Ericsson, and furthermore, we also get supported by the IT center of the university because they own all the fibers which we are using to connect the different sites. So that's a little bit the framework which we are using, and you see a little bit the technical framework. But as mentioned, Niklas will be explaining a little bit more about the architecture. So the 5G Industry Campus Europe has different fields of activities, different markets. So manufacturing is actually where we are coming from, and also logistics is part of the 5G Industry Campus Europe. But as we are using also outdoor networks and also dedicated cells for special purposes, like in construction, for instance, so where we are having activities with other researchers here on the campus of the university. And so we are addressing different verticals like mobility, energy, construction, and also health. So the activities in the 5G-ACIA endorsed testbeds, as mentioned, that was focusing on sensor technology. And the sensor technology in manufacturing is quite often focused on monitoring of machining processes, because machining is where value chains start today. And therefore, since the manufacturing tasks are, let's say, becoming more and more challenging, it's helpful to have additional monitoring capabilities in order to find out the sweet spot of each manufacturing process, where it's still capable to manufacture what you need to manufacture, but you do it as economical as possible. So that means low scrap rate, of course, and but also have short cycle times and short production times. So that's always a little bit the conflict where you will need to find the sweet spot here. And monitoring technologies are actually key in order to find this kind of sweet spot. And we developed different sensor technologies which can be used to monitor the processing, so the actual manufacturing process, like milling, for instance, but also things like tool conditions, or the cutting tools, which are consumables and cost factors of factories today. And so we dealt with how to monitor the condition of the tool, for instance, wear condition or tool breakage, and so on. So one concept or one common architecture we implemented is having the physical setup. So that's the sensor element, but also the hardware with the electronics and the 5G user equipment, having this positioned inside the machine. And since we are dealing mostly with 5-axis manufacturing technologies, it ideally has to be cableless, so wireless. So this kind of physical quantities will be acquired with a sensing element. Then we have different signal processing steps which are embedded on the same device. So we have some microcontrollers that can do the processing. And at the end, we also have the 5G UE is integrated into the sensor box, and also, of course, a battery. And the 5G UE can wirelessly transmit the sensor data, and then perhaps process this on an on-premise edge cloud, or directly send the data to the machine, not necessarily via the 5G link, because the machine is typically not a mobile device, but it has a cable connection, and so therefore it makes sense to use the local breakout function of the user plane as part of your 5G system to transmit the data to the different targets. That may be, for instance, a machine tool or just a database on the edge cloud for storing a digital twin. And with that, we started in 2021 already, and the testbed is finished, so all the results are there. And the testbed members are Ericsson, Fraunhofer IPT, u-blox, from which we tested a very special chip for generating accurate timestamps, and Marpos, which is a sensor company from Italy. So now I'd like to hand over to my colleague, Niklas, who will explain a bit about the technical setup of the 5G Industry Campus Europe. So Niklas, please.
Okay, good afternoon, everybody. Thanks for joining also from my side. My name is Niklas Beckmann. I'm from the Fraunhofer IPT as well. And let's have a quick look at the architecture of the 5G Industry Campus Europe. What Niels already mentioned is that the 5G Industry Campus basically consists out of 4 different 4G, 5G sites. There we cover approximately 1 square kilometer. Yeah, on this graphic you can see the different members of the campus. There's the WZL, the Werkzeug Maschinenlabor of the RWTH Aachen University, the Fraunhofer IPT, the FIR, the IT Center of the RWTH. And also that was already mentioned by Niels. We also have 3 indoor shop floors, which cover approximately 8,000 square meters in total. And depending on the size of the shop floor in each of these, we installed 4 to 8 radio dot pairs. We utilized the spectrum between 3.7 and 3.8 gigahertz, which is the N78 band, and typically reserved for industrial use. Obviously, we have the 100 megahertz, and since we were talking about non-standalone, we also have the 4G LTE anchor band, which is at 2.3 gigahertz, and there we have a piece of the spectrum of 20 megahertz. Yeah, you can see on the graphic also that the Fraunhofer IPT is the largest, the main course size of this industry campus. We have it serves as an entry point for data which is routed from outside of the network into the network of the IST center. And also, as you can see on the graphic, we have the home subscriber server and the operation support systems located here at the IPT. Now let's have a deeper look at the infrastructure of the testbed here at the IPT. As I said, and you can see it on the graphic down here, the IPT hall is around 90 meters long and 30 meters wide. We have 8 radio dot pairs installed, which you can see in yellow on this graphic. They have 20 meters of distance to each other. And as you can see on the other picture on the left-hand side, it's located 6 meters high. Yeah, these radio dots are then connected via Cat6A or beta cables with the 4G and 5G indoor radio units, which are then connected to the baseband generation. And the baseband generation is then connected to the router, and the exercise of router is obviously to route packets from the NSA core or into the NSA core from the network. Additionally, we have at the shop floors, we have installed local breakout points. The reason therefore is to lower the latency basically, so that packets don't have to be routed throughout the entire network, but can be caught basically directly at the breakout point. We reach latency up to 8 milliseconds there, and in the downlink and uplink, depending a little bit of course of the location, we have 940 megabits per second on the downlink and 85 at the uplink. I would advise you, if you are more interested into details, you could have a look at this paper, which is given down here. Just follow the link and you will see it. Okay, now let's get practical. I would hand over to Niels again for the live demo now.
Okay. Yeah, it's okay. So thank you, Niklas. I hope you can hear me and see me. So we are now here in the area. So I'd like to show you 2 sensor systems which we developed in the 5G-ACIA Endorsed testbed. So the first one is the multi-sensor platform, where we have the capability of measuring different physical quantities like acceleration, temperature, strain, for instance. And here we have one accelerometer. It's a piezo-based element which we can fit inside the machine. So typically we position it at the clamping device of the machine. And this accelerometer can capture any, let's say, vibration that is coming from the machining process. So then we have a small box containing some PCBs. One PCB is a microcontroller board. The other one is for acquiring the sensor data, and below that is also a 5G UE and the battery pack. So this box would be typically running inside the 5-axis milling machine. So now if we have any kind of physical events happening, like vibration are induced by the milling tool to the workpiece, then we can actually record this, send it via the 5G link. And from the 5G system, so the 5G core network, it has a user plane function. So that means the data can be routed into the cabled network. So the local area network, which we have on the shop floor. And we have a small PC that is receiving this kind of data stream and plotting it here on the screen. So now if I induce any noise or any vibration on this device, and you are able to see it, so you may hear it as well, because we disable the noise cancelling, and you can see that the reaction is really quick. So here you see this vibration spectrum. So the sensor box is doing the bus Fourier transformation calculation, and also we see the amplitude over frequency, and then we see a time series of the vibration amplitude, where you can detect if there is anything happen at all. It is also important to understand what is the machining time and where's no machining time. So this kind of platform can be used to record all the sensor data during the machining process. And if we synchronize the machining data, so like the positions of the machine, the milling tool, for instance, then we can synchronize the sensor data with the position data and create, for instance, a digital twin where you can map the vibration amplitudes over the geometry of the part. So, but we have another sensor system, which I'd also like to show it to you. So in theory, it's quite comparable. It's very similar. Also, here we have a piezo element, but now we are interrogating this kind of sensor with a very high sampling rate, 1 megahertz. And before that, we had 20 kilohertz. So now we are in the range of so-called acoustic emission, which is actually, let's say, an acoustic fingerprint recording of the solid body. So as soon as we have any physical contact between metal and metal, then we can measure it. And this kind of interaction, of course, we have between the tool and the workpiece. Again, here we have some electronics for the signal preconditioning, and there's an FPGA for the signal processing because we have a high computation load because of the high sampling rate. And then again, we have a 5G user equipment, which in our case is then an external device, but it could also be an integrated device. It doesn't play a role. It's just a different form factor. Both cases, we have Ethernet as an interface between the sensor board and the UE. So now if I generate some physical contact, now we have a drill, an old drill, which is artificially outworn. And if we have the physical contact, and you can see in the waterfall plot, on the y-axis we have the spectrum, and on the x-axis we have time. So you can see each acoustic fingerprint of each cutting edge. So this acoustic fingerprint could be utilized to train a model for wear, and wear is actually a cost factor, and therefore it's attractive to monitor this kind of condition in real time. And so a wireless sensor system. Why a wireless sensor system? Wireless sensor system also in this case is beneficial because you can easily retrofit this kind of sensor system and put it inside the machine to do your trial, and then take it out and go to your next machine. So I hope this was interesting to you, and so that's it from my side, and waiting for your questions in the chat. Thank you.
Thank you very much, Niels. Now we are switching for the next call. Right, Niels, you already received 2 questions. You will have to wait for them a couple of minutes, because first we are going to hear from Gustavo Cainelli and Javier Velasquez about the testbed on PROFINET and PROFIsafe transmission over 5G. And without any further ado, the floor is yours, Javier.
Thank you. Thank you, Lisa. Do you see all my screen? I'm sharing. Okay, good. Thank you very much, everyone, for being here. Javier Velasquez from NXP will present you our testbed for analysis of the performance of 5G networks for PROFINET and PROFIsafe data transmission. Right here with my colleague Gustavo from IFAC, and before we continue with more details and more data about us, my first question to you would be if you are familiar with PROFINET and PROFIsafe usage in automation systems. So I guess Fabian will help me to put there. Yeah, here you have. Getting more participation. And well, the idea of this question is to get how good and how well do you know the topic of this presentation, where mainly people is in the area of partially knowing or knowing about it. So it's good to know, because well, that would facilitate some of the conceptualization and understanding of the topics here. So for yeah, most of the people here is partially related to the usage of PROFINET, and well, in general, we would be fine with going with not that much detail on the technicities, but on the results of the testbed. The outline for the presentation today will be yeah, showing the objectives of our testbed, the setup itself, how it was implemented, and finally, Gustavo will give you an overview on the results and the dissemination activities that we have reached here. So the members of the testbed, all of them are part of 5G-ACIA, IFAC Institute from Germany, HMS Networks, NXP Germany, and Radisys. So before continuing there, the first step would be, yeah, explain why we decided to do this analysis of PROFINET over 5G. Well, we consider that functional safe wireless communication can be widely used in industrial automation, right? So that makes one point, and the other point is that PROFINET and PROFIsafe are very popular protocols for real-time communication and safety applications in industry. So considering these two big topics, we ask ourselves a set of questions that will be addressed in this presentation. However, before jumping there, we have again another set of questions, which it is about the relevance of these technologies for self-based communication in your business. So how relevant is for your business to enable or implement fail-safe automation solutions? So is it relevant? Not that much, or maybe you don't know. Nice. Well, it's quite evident, but for most of us here is a relevant topic. The fail-safe applications are more and more necessary for the different automation processes, and well, interesting to know that that we have some of our participants who don't know if this it is important or relevant. So let's help to figure out how helpful would be the fail-safe applications over 5G. So to state the objectives of our project and the testbed, we started with some key questions in the team. So, for example, which conditions on the communication link would allow to achieve suitable response times for safety and fail-safe application? Other question, for example, is what are the capabilities of a 5G system to transmit PROFINET data, right? And of course, if it is this kind of applications would be feasible on 5G networks. So based on those, we set these two big objectives, which is, first of all, achieve a comprehensive understanding of the overall network behavior related to real-time behavior of the protocols, and also the consequences of the network behavior on the fail-safe applications, right? And the second big question is, or the second big objective is to do a pre-deployment analysis of the feasibility of the fail-safe communications over 5G, right? So based on that, we got our testbed prepared and endorsed by 5G-ACIA almost 2 years ago. And this was approved to, I mean, with the general objective of measure the performance and evaluate this performance of a 5G non-public network for PROFINET and PROFIsafe communication, right? And to achieve this implementation, each of the members of the testbed contributed with some of the parts. So for the measurement and evaluation, IFAC is doing its part, providing some of the equipment for measurement and also providing the experience and expertise in the analysis of network and industrial communications. The 5G network is provided by NXP and Radisys, a combination of hardware and software provision. And for enabling the PROFIsafe communication over the 5G network, we are using technologies from HMS, which essentially provided the devices for tunneling the traffic through the network. So here on the schematic overview on your right, you see the different components of the network in this simplified layout. And the bottom, you see the measurement equipment. It is the multi-phase devices by IFAC, which allowed emulating and let's say injecting different types of traffic, in this case PROFINET traffic in the system to be measured, and also provides the capability of a really accurate time-wise measurements with the granularity even of microseconds, right? On the second point, we have the tunneling of the communication, but we're using HMS technologies. In the next slide, I will show you a little more detail about it. Finally, we have the 5G network as set, a combination and cooperation between Radisys and NXP for providing hardware and software in the 5G system. So here is maybe a little more simple and meaningful for all of you to understand how this was implemented. So we have two end devices performing PROFINET communication. We have on the top PLC, which is the PROFINET controller, and in the bottom PROFINET input-output device. And in between, of course, we have our 5G network. However, to enable this layer 2 communication over a 5G link, which is IP based, we need to tunnel, or let's wrap the PROFINET protocol to make it go through without any inconvenience. And that's achieved with the components here signal as PROFINET gateway and wireless bridge for 5G. Right next to the PROFINET devices. So the objective and the right, and I mean the I forgot the word, but the essence of these two devices is to create this wrapping of the communication. And of course, in the end, we have our measurement devices, which are in charge of evaluating the different test groups. So in our test bed, we have three different alternatives for test groups. The first one is to do a measurement of the 5G communication only between the UE and the core network. The second test group option is to do an emulated PROFINET traffic over the 5G network that would be measured between the UE and the PROFINET gateway, almost next to the PROFINET controllers. And the third approach is to measure the communication purely between the two PROFINET devices. So for our testbed, we follow the two last approaches, test groups that Gustavo will explain in the next section. So yeah, the floor is yours, Gustavo, and please.
Thanks, Javier. Thank you very much. So I would like to talk with more details about the setup and the test system that we have here. So we conducted measurement campaigns and we tested several test cases. And today I would like to talk about two test groups that contain some test cases. The first one is we called minimum transfer interval, and we tested only the 5G system using our multifaces that are the devices developed by IFAC. The multifaces, they can emulate PROFINET. So we used them to emulate the PROFINET data over 5G. And we tested, our tests are based on logical links, which are communication relations with a source and a target. In this test group, we tested different minimum transfer intervals. Can you click, please, Javier? Yes. So the transfer interval is the time between messages in the source. So we conducted in this test group many test cases with different transfer intervals to test the limits of the communication system. And some of our metrics, also known as performance parameters, are, for example, the transmission time or the latency, and the update time. The update time is the time between two consecutive messages in the target. So we tested in both directions, downlink and uplink. And I would like to show you some results of these tests. As I said, we conducted many test cases, and here I bring some results. In the table, you see 6 test cases where we tested uplink and downlink with different transfer intervals from 53 milliseconds to 7 milliseconds. The table shows many results of minimum, maximum values of transmission time, update time, but I would like to highlight some results like the P95 value. That is the same you see in the bullet points. The P95 value means that 95% of the message arrived below this value. So, for example, in the chart in the left-hand side, you see a distribution that's concentrated close to 10 milliseconds. And the P95 value is 8.2 milliseconds, which means that 95% of the message arrived in the target within or with less than 8.2 milliseconds. For uplink, we have a value a little bit higher, that is 34.9 milliseconds. And this difference is expected because we have a TDD ratio of 4 time slots for downlink and 1 for uplink. So we expected that we would have this difference. Can we go to the next one, please? Yeah. So the second test group, then we evaluated PROFINET and PROFIsafe over 5G. And in this test group, we have 2 test cases. One is a wired connection, and another one is a wireless connection. So in this case, our test system acts a little bit different. We have one multiface acting as traffic generator, giving inputs to the PLC. And these inputs, they are sent to the PROFINET I/O device or the PROFIsafe I/O device. And next, please. Then we use another of our multifaces to monitor the traffic. And in this case, the multiface is monitoring the PROFINET traffic. We see here in this switch, there is a switch with port mirroring, which means that all message that the PROFINET I/O device, the PROFIsafe I/O device, sorry, this yellow one at the bottom, all the message that this device receives, the multiface also receives that. The multiface can open this frame and analyze all the fields and can see if the message that left the controller arrived correctly to the device and what is the transmission time, what is the latency for that. We did that using a cable, and without a cable, we're using the wireless communication system. And I want to show you the results in the next slide of this comparison. So for this comparison, we bring here 2 charts that shows the transmission time, the histograms of the transmission time for uplink, for the downlink. And in the left-hand side, you see the wired connection, and in the right-hand side, you see the wireless connection. You see that the wireless one, the distribution, there is a shift to the right-hand side, which is also expected. It's a delay added by the communication system. This distribution, even for wired connection, is a bit wide because the multi-phase, we are also considering here the communication cycle of PROFINET, which means that all the inputs that the controller received, they are sent to the PROFINET IO device only every communication cycle of PROFINET. And in this case, it was 32 milliseconds, the communication cycle. In the right-hand side, you see the histogram for the wireless one, and you see that the distribution is quite similar. There is this shift to the right, accordingly to the delay of the 5G system, but there are also some outliers. These outliers is something that must be investigated because this may cause issues to the PROFINET system. Can you go to the next one, please, Javier?
Is it this one? No. Yeah, this is the.
Can you? Yeah, sorry, I think I had a connection issue, but I think you hear me now, right?
Yes.
Okay. Yes. So yeah, I was saying that we tested these 2 test groups, and we also exhibited our test bed in many conferences and fairs, as you see here, for example, Hannover Messe, Chicago, also the 5G Industrial Days in Taipei last year, and also in some scientific conferences, as you see here, our colleague Harsha in the ETFA last year in Romania. In these fairs and conferences, we got some feedback from some specialists and from some interested people about the topic. And now we have another pool to get a feedback from your side. So do you think wireless communication technologies are mature enough to support safety critical industrial automation? Okay. Interesting result. We have, okay. Yeah, we have 44% that says it's partially and 36 that yes. So it's an interesting result. And I would agree with you. I would say that yes. But of course, there are still some challenges that still need to be investigated. And this is one of the objectives of our test bed, is investigate these challenges and check if 5G or other wireless communication systems can really cope with this kind of safety application. For this reason, I would like to highlight the importance of performance testing as we are conducting here. So just for summarize and close this presentation, we presented some test cases that evaluated the performance of 5G to transmit PROFINET and PROFIsafe data. The first test group, we evaluated only the 5G system emulating PROFINET data. So our multi-phase is emulating PROFINET data. The second test group, we then used real PROFINET and PROFIsafe setup, and we compared the wired and wireless case. We identified that the 5G system, for some cases, especially for downlink, can add around 8 milliseconds of latency in the downlink direction. And we conclude that it's possible to transmit PROFINET and PROFIsafe data over 5G. But of course, it's necessary to analyze this, the time behavior to identify what is the best configuration for the PROFINET system. And then that's it. Thank you very much.
Thank you very,
Thanks
yeah,
for your
very
attention.
much.
Thank you, Gustavo. Thank you, Javier. So there's some virtual applause. Again, thank you, Niels. Thank you, Niklas and Gustavo and Javier. Also for the excellent time management, not only for the excellent talks. We received some questions, and I would like to start with a very technical question directed at, I guess, Gustavo, about how the PROFINET controller was configured. Which cycle time did you use? What stock settings were chosen? Can you very briefly give some input on that?
Yes, we configured with a communication cycle of 32 milliseconds. As you know, we could, for example, configure with 1 or 16 milliseconds, but analyzing first the 5G system, we identified the boundaries, the range of the latency, and then we configured to 32 milliseconds.
Okay, thank you. I hope that answered the question, Frank. Maybe a question directed to everyone. Did anyone experience problems with jitter?
Yes, actually, as I mentioned in the beginning of the presentation or in the middle of the presentation, we measure the transmission time and the update time. And specifically talking about PROFINET, the update time is even more relevant than the transmission time. And during our tests, in the initial phase of our measurement campaign, we identified some outliers, as I showed you in the results, some outliers caused by the communication system, the 5G communication system. And these outliers, they caused problems with the PROFIsafe communication. So the jitter caused problems, but specifically when we had this kind of outliers, in the distribution.
How did you deal with that?
We had to be able to test. We had to increase some timers of the PROFIsafe system to make it more resilient. And during after the measurement campaign, some upgrade was done in the communication system, in the 5G system, to try to debug and to eliminate these effects.
Okay, so the measurement helped to reduce the jitter.
Yes.
To diagnose.
Yes. Right.
Diagnose it,
Niels,
especially.
Sorry, Javier.
No,
Niels, what about
go ahead.
jitter in your testbed or in your applications?
Yeah, so we're not so much investigating the jitter in the standard testbed, but for the TSN testbed, which maybe you have seen in the corner, which is a special setup, and so the statistics that Niklas has shown about the performance was just one diagram from a publication, and there we also investigated this so-called ULLC testbed, which is implementing parts of TSN over 5G as a prototype, of course. And and there we also experimented with FRARE, so the frame replication method, which helps in terms of achieving or decreasing the jitter and latency in a certain confidence interval. And so as part of the results, I think we have shown this slide, but we can maybe show it again.
Yeah, go ahead.
Compare the performance, and I think it's also addressing a little bit another question that came into the chat. So maybe Niklas, do you want to say something about it?
Yeah, as you
Maybe
can.
first, the other question. The question is, what is the average or the guaranteed latency in the system?
Yeah, the question about guarantee latency is basically in what confidence interval means guaranteed. In this case, we provide the graphic from the paper that's also written on the slide below. And what you can see is that with a 99.9 percentile, we can say that for each of these different use cases, so MBB or ultra reliable, low latency, and so on, the latency is in these intervals.
And it's also comparing different UEs. You see also a little bit of an influence depending on the UE. So that's also something where you do not have a clear answer because it depends on the actual setup and which UEs you are using. The right bar that you can see here, that's the mentioned ULLC testbed. And here the jitter, we measured the jitter for this explicitly, that was 3 microseconds. But of course, it's a prototype system, and you cannot really compare it to commercial deployments because you do not have this kind of performance in a commercial deployment, I guess. And of course, for this measurement, the network is basically unloaded besides the UE under test.
And latency refers to downlink in this case, uplink latency.
Yeah, this was a uplink latency for package size of 100 bytes. But in the publication, there were also results giving for 1024 bytes, both for uplink and for downlink. Not surprisingly, the downlink latency was less because still all the deployments are more downlink friendly, unfortunately.
What was the network for these the configuration of the network for these measurements? Do you recall them? TDD ratio wise?
I think it's a so-called vanilla flavor. What is it? 4 times 1? 4 downlink and 1 uplink for the ratio.
Okay. Niels, a follow-up question. As you mentioned TSN, there's also a question in the chat. If you could share some perspective on real-world implementations of 5G TSN or 5G DetNet integration.
Yeah, okay.
Do we have it?
Yeah.
When is it expected?
Yeah, that's a tough one, I would say. It's having multiple factors. On the one thing is market availability. So it's on the one hand, you need the chipsets that need to support TSN. They're not yet on the market. And then furthermore, there's some noise. I hope you can still hear us. So we are on the shop floor, sorry. So the market availability of chipsets that support TSN, so that's of course not yet there. And on the other hand, you need a market request. So I think also on a shop floor with all the automated systems, you do not find TSN so much. So PROFINET, PROFIsafe are much more widespread than TSN. So there's especially in Asia, there's the CC-Link IE over TSN as a field bus communication method, which of course uses TSN. We have experimented with that, and yeah, so the results are actually quite good. And as mentioned, adding FRARE on top to increase the reliability. So that's I think looking promising, and I guess I think that as soon as there is a market demand for TSN equipment, then so the ICT and OT vendors, they know how to do it. Right? So that's not so much of a miracle how to integrate TSN and 5G. And DetNet, I think it's still a little bit in the trial phases. So we're also trialing DetNet as well, but we cannot share any results. So to answer the question, real-world implementation, you do not find this kind of real-world implementation only in trials.
Looking at the time, maybe a final question. First to Niels, about the transmission reliability. That's also something that we have interest in. Did you measure that? What did you experience? This message losses.
This one goes to the second testbed, I guess.
You can go first, Niels. And then I will ask.
I leave the stage to Gustavo and Javier.
Okay.
Gustavo, you are muted.
You're muted.
Sorry.
Nice.
You mentioned about yes. You mentioned about the message loss ratio.
Mm-hmm.
Yes. Yes. We also measured our test system is, let's say, message based. So we measure for each sent message transmission time, update time, and of course if the message arrived or not. Unfortunately, I didn't show the results for message loss ratio here in the tables, but of course we have measured that. We saw that for some cases when we decreased, for example, the transfer interval to values like 10 milliseconds, 8 milliseconds, 5 milliseconds, we see an increase in the message loss ratio. So probably messages are in a buffer somewhere in the network and some are dropped. But unfortunately, I didn't put in the presentation the results for that.
Okay, very final question. Maybe to Javier, which tunneling protocol was used to transfer the messages over 5G, the safety messages?
Well, Gustavo, do you remember the exact name of the? It's kept to my mind right now, but you remember the protocol used in the tunneling?
Yes, yes. The protocol that is used in the tunneling is VXLAN. VXLAN because 5G or the 5G system we have is IP based, and the PROFINET is layer 2. So we used VXLAN devices or the VXLAN protocol to tunneling this data.
Perfect. Thanks. Thanks again to the speakers. Thanks for the time management. We have 1 minute to 3. We're bound to close the session now. If you felt that was helpful and you gained some information that was useful, I'd like to invite you to the other 2 upcoming web seminars, which are also free of charge, but please register. You will find the links here. We can put them to the chat, and after your registration, you will receive the link, as you already know. So we are looking forward to seeing you again on March 19th. Thanks again for joining, for taking your time, and have a nice afternoon, a nice day. Bye-bye.
Thank you all. Bye-bye.
Thank you.
Bye-bye.
Bye-bye.